Alright, so let's talk about one of the biggest topics that we're going to see here in its hypothesis test of proportions. So we're going to talk about a whole bunch of different things today. You have to really follow it to really get it down, but it's a hypothesis test about proportions. And the best thing to look at is basically kind of look at it as from one situation and just break it down by the steps. So let's look at the situation here. Giant Foods in Dundalk claims that 93% of these other customers approve of the way that the store is managed. Not fully believing this, an individual decided to run an experiment and decides to poll customers as they leave the Giant. So many English errors. It's really supposed to be there too. Leave the Giant. He picks 500 random individuals and discovers that the percentage of satisfied customers is actually 90%. Is this enough evidence to prove that the satisfaction of the customers is different from what is stated? Now, before I even go into this process, there's a population parameter and there's a sample statistic. So there's basically a p, which is the population, and a p hat. I'm not going to write the p hat though, but population parameter is 0.93 because the 93% is the population of people who go to the Giant. The 90% is based off the 500 random individuals that this particular person was doing the sample off of. So, and that's going to be important because you need to know what the P is to do most of our calculations in here. Now, the easiest way to look at a hypothesis test is to kind of look at it as a court case. So basically we're going to attempt to disprove a form of parameter to see if they have changed over time. And again, it's easier if it's simpler to look at it as a court case. So let's just take a look at it. Step number one, we're going to present initial evidence. Before a case can begin, the prosecuting lawyer has to prove that there is a case. Essentially, that they must show that there is a justification to holding trial. This is the first step in our hypothesis testing process. We have to provide evidence to justify that we can do the hypothesis test. So the three pieces of evidence that we show is that the sample comes from a random source, that the sample is less than 10% of the population, which is one of the qualifications we saw for a sampling distribution, and that the n times p is greater than or equal to 10, and 1 n times 1 minus p is greater than 10. So essentially two of these are just showing you that it's a sampling distribution, and then the other one is just showing you that it comes from a random source. Well, what does this look like? Well, remember this is our situation about Giant right here, and we know that our p is equal to 0.93. Well, if I look at this and take step number one rather, I need to show three things. One, it comes from a random source, which we'll just label it as random. And this is probably the one thing I sometimes forget to write in, is that it comes from a random source. So I always tell my students, just assume that it does. But you can see right here that he took 500 random individuals. So all we have to do is say that 500 individuals were taken at random. Okay, and then we have our 10% condition. Say 500 times 10 is equal to 5,000. And essentially what we're going to say is 5,000 people are less than all the people who would go to this particular Giant. I'm assuming that that's true. I'm not going to sit outside and do a survey on all the people who go in, so I'm just going to assume that it's true. 5,000 people. I think it's reasonable to assume that. Less than all people who attend this Giant. 3, success, failure. So what we do is we say n times p has to be greater than equal to 10. So the n is our 500 that we've been using the whole entire time, and our p, which you discovered in the very beginning, is 0.93 in this case. And so we quickly do 500 times 0.93, and that gives me 465. Oh, you have to ignore the horn beeping outside. And that's greater than or equal to 10. And then we're going to do 1 minus 0.93, which is 0.07. When I really set this place up, I'm going to make sure all the windows are closed. But that's 1.93. So let's see. That gives me 35, which is greater than or equal to 10. And so with those three things working out, that means we can actually do our hypothesis test situation here. So we're going to move on to step number 2. So step number 2, after the lawyer proves he has a case, the trial starts. On the day of the trial, both lawyers present opening arguments where they state what they're attempting to prove, something. That's what we're going to do. So we have to, it's the same thing for our hypothesis test method. We end up with 2 different hypotheses, the null and the alternative hypothesis. The null just states the original parameter is what it is, basically what it is, what the probability currently is. The alternative could be slightly trickier because it's either going to be less than, not equal to, or greater than, based on what we see in that last question. So let's apply for this real fast. So here's our situation again. If I look at step number 2, so what I have here is null and the alternative. So H sub 0, H sub A. H sub O stands for the null. H sub A stands for the alternative. Okay, so my students have expressed that it's like laughter because you have ho and ha. Like when Santa laughs, ho ho ho. When most people laugh, it's ha ha ha. So, that's kind of a way to memorize it. But we're then going to write P. Now, the null hypothesis is always going to be P equals, and whatever it is that you start off with. So we had a P of 0.93, so it's going to be 0.93. Then the alternative hypothesis is going to be either less than, greater than, or not equal to, based on what you read, because you can't base it off the other percentage. If you look at this and base it directly off this percentage, then you're never going to have a situation where it's not equal to. It would either be less than or greater than. So you have to kind of read what it's asking you to do. It says, is this enough evidence to prove that the satisfaction of customers is different? And different is kind of a neutral word. Doesn't mean less than, doesn't mean greater than. It means not equal to. It's a neutral word. So what we're going to do is we're going to go and say this is not equal to 0.93. And that is my step 2. Okay. So now, what about step number 3? Step number 3, after the opening arguments, the lawyers then present their findings in hopes of coming to a favorable conclusion. For a hypothesis test, we will do the same exact thing. Basically, you have to calculate the standard deviation and then calculate the percentage based off the z-score. Once you find the percentage, this is where the alternate hypothesis comes back into play. If your alternate hypothesis is less than, then your percentage is the p-value, which is the same thing as when you're calculating a normal curve anyway. Same thing with this one. If your alternate hypothesis is greater than, then you have to subtract your percentage from 1, and this is your p-value. The one that's really different right now is the alternative hypothesis being not equal to, which is what we have in this situation. What you would do is you would multiply your percentage by 2. And then this is your p-value. So let's apply step number 3. So we're going to go here, and the formula that we're going to use to find our standard deviation is the same one as the standard deviation from the sampling distribution in our confidence intervals. So we're going to use the square root of 1 minus p times p over n. So we got the square root of 1 minus 0.93 times 0.93 over 500. So I do the quick calculations. Oh, that rain's picking up outside. I might have to close that window so it's not overbearing my voice. It probably isn't. I'll reshoot if I have to. And so if I do it, I end up with a 0.0114. Okay, so now I'm going to look at a normal curve formula. So we're going to do so the x is actually the alternative, the other, the sample proportion. So if we go back here, we haven't used 90 at all yet. This is where the only place where it's going to come into play. So we're going to do 0.90 minus 0.93 divided by the standard deviation of 0.0114. So if I do the math, it would be negative 2.63. Okay, and so I'm then going to look this up into my z-chart. So if I look at my z-chart real fast, I'm looking at negative 2.63. That gives me 0.0043. Okay, so now what's going to happen is this. I'm looking at my alternative hypothesis right here, and it says not equal to. So another rule is if it says not equal to, we're going to multiply by 2. So we're going to get 0.0086. And this is my p-value. This is probably the most work we had to do the whole entire situation. Okay, the last step, because there's 4 steps. Step number 4. So the jury deliberates and determines if there is enough evidence to convict or not, and they render a verdict. If they feel that there's enough evidence to convict, they submit a guilty verdict. If not, then it's not guilty. It's important to note that they're not saying that they're innocent. We do this with a hypothesis test. So as a standard, we weigh this against 0.05. We're going to talk about why in a second, but we're going to that's what like our standard is. If the p-value is lower than 0.05, then we say that we have enough evidence and we reject the null hypothesis. This is basically very similar to a guilty verdict. If the p-value is greater than 0.05, then we say that we have enough evidence, and we don't have enough evidence rather, and we failed to reject the null hypothesis. And we can think of this as a not guilty verdict. The important note here is that we don't ever accept the null hypothesis. This is a difference between not guilty and innocent. Saying someone is not guilty is not saying that they didn't do the crime. It only says that there wasn't enough evidence to prove that they did the crime. So that's why you never hear people say someone is innocent. You always hear it's not guilty. You're basically saying when someone is not guilty that they just don't have enough evidence to prove their guilt, which is important because plenty of people who are guilty are never sentenced. So it's a thing that happens. Now, here's a question: why is 0.05 our standard? Well, that's where we consider things to be statistically significant. And statistically significant means that something's happening. That something that's happening is not due to some kind of random chance. When we say it's not happening out of random chance, we're saying that it's happening for some kind of reason out of the normal occurrence. Now, why is 0.05 the one that makes it statistically significant? Well, basically, if you go back to when we started talking about a normal curve, we had a mean, and we had 1, 2 standard deviations out, and we say anything beyond 2 standard deviations would be statistically significant. And so what is 2 standard deviations? Well, that's 95%. So how much is outside of 95%? 5%. So that's why the standard is 0.05. 5% is 0.05. Okay. So let's go back and apply step number 4 to our situation here. So we got step number 4 here. We had a p-value of 0.0089, so 0.0086. And we're going to compare that to 0.05, and in this case it's less. So what's going to happen is I reject the null hypothesis. Okay, and then what I do is I actually answer the question here. So the question says, is there enough evidence to prove that the satisfaction of customers is different from what is stated? Well, if I rejected the null hypothesis, then I have enough evidence to show that there is a difference. Let me just double check. Difference in customer satisfaction. There's a difference in the satisfaction of customers. And that's it. That's the whole hypothesis. The whole hypothesis, what's the word I'm looking for? Formula. No, that's not the word I'm looking for. The whole hypothesis way you do it. Method, that's what I wanted. The whole hypothesis method. Okay. So let's take a look at a second example. Situation 2, in a certain state, the percentage of males born account for 48.5% of the babies born at any given time. A sample of 700 babies is taken at random from all the local hospitals, and it's found that 50.1% of these babies are male. Does this give enough evidence to show that the percentage of male babies has risen? Okay, so first off, before I start this whole process, let's take a look. I have a 48.5% and I have a 51.1%, but the 51.1% is based off the 700 babies, so that means that this is my P, this is my N, and this is what's going to be used at the very end. Okay, so let's do it. So we got step number 1. So first we're going to do is do random. So random, we are working with 700 babies, so 700 babies was taken at random. It's kind of a weird sentence. You're not going to ever take babies, but you know what I'm trying to say. 10%. 700 times 10 gives me 7,000. I'm fully willing to believe that 7,000 babies is less than all the babies born in this area. let's see. Then my P is 48.5. So I'm going to change it into 0.485 and do my success failure. So 0.485 times 700 gives me, where is my calculator? 0.485 times 700 gives me 339.5, which is greater than or equal to 10. And then I have to do the opposite, 1 minus this. 0.515. So let's see. That gives me 360.5, which is greater than or equal to 10. Remember that this is just 1 minus 0.485. Okay, and so this says I have enough to do my hypothesis test, so I move on. And so now I have step 2. Remember, I have 2 arguments. I have the null, and I have the alternative. The null states that 0.485 is the average for the population, or really it's the average proportion, but that's the same thing. And then for here, if we go back, it says, does this give enough evidence to show that the percentage of male babies has risen? Risen means go up. Risen is greater than. So I'm going to say that it's actually greater than 0.485. Okay? And that is my hypotheses. Step number 3. Square root of 1 minus p times p over n. So let's see, I got 1 minus 0.485 times 0.485 times 700. So that gives me 0.1889. Okay, and so now I'm going to go back and get my other percentage, which was 50.1. So I'm going to do 0.501 minus 0.485 divided by 0.1889. And let's see, 0.084. Actually, wait a minute now. Something's not stirring the mustard there. I think I made a mistake somewhere. Hold on one second. Let me go back. Times 0.485 divided by 700. Yeah, that should be a 0. 0. Let's go back here. 0.501 minus 0.485 divided by 0.01889, and that's a little bit better. I knew that wasn't right when I saw it. It's 0.84. Okay, and if I go real quick and look up my z-score, let's see, 0.84 corresponds to 0.7995. Now, when I go back here, my alternate hypothesis was greater than. So that means I'm going to subtract from 1. So 1 minus 0.7995 gives me 0.2005. And so that is my p-value. Okay. And then just double check everything real fast. I think this is a little bit different than I had because I extended that out. Yeah, I think it's fine. Okay. Finally, for step number 4, so 0.2005 is greater than 0.05. So we, or rather I, fail to reject the null hypothesis. And I do not have enough evidence to, and let's just go over here and see what we're trying to prove, give enough evidence to show that the percentage of male babies has risen. I do not have enough evidence to show the percentage of male babies has risen. Okay. All right, we got another one more situation here. Situation number 3. The pass rate of a certain professor at Towson University is 78%. A student decides to conduct an experiment of 700 randomly chosen former students of the professor, and determines that 77% of them were able to pass one of the professor's classes with, and determines that 77%. Okay, sorry, lost my spot. To pass one of the professor's classes. Is this enough to show that the professor's pass rate is less than previously thought? So let's take a look at it. Which color am I going to use? We'll go back to the old colors. So well, first off, before I do steps, remember this is P. This is based off the population. 77 is based off the 700. Okay, so we're going to look at this and say step number 1. And we had how many? 700, so 7, so random. 700 students were chosen at random to 10%. 700 times 10 equals 7,000. This one might be a stretch. I don't know. I'm a teacher, and I've probably seen more than 7,000 students in my lifetime, but it might be a stretch. I don't know. But 7,000 students is less than all students this professor will teach. And then success failure, so we've got 78%, yes, so 0.78 times 700 is 546, is greater than or equal to 10, and then 0.22, which again is 1 minus 0.78, times 700, and that's equal to 154, which is greater than or equal to 10. Okay, and then with all those things, we can now do our hypothesis test. Step number 2, we have our null and we have an alternative. So we have P equals 0.78, and if I go back real fast, it says, is this enough to show that the professor's pass rate is less than previous thought? So P is less than 0.78 because we're going to be less than. Okay. Step number 3. Okay, so I now have to go ahead and do the square root of 1 minus p times p over n. So it's 1 minus 0.78 times 0.78 over 700. And let's see, that gives me 0.0157. So 0.77 minus 0.78 divided by 0.0157, and make sure you remember that this one is the one based off of the statistic. So that's a 77%. That's the other percentage that that we had before. So if I do the math, I get negative 0.64, and then again if I jump over to my z-score chart, so I get negative 0.6, so 0.6. 4. So that's 0.2611. Okay, and so don't need this anymore, and so I get that, and it's less than, so leave alone. So now step number 4, we'll use pink this time. Step number 4, 0.2611 is definitely greater than 0.05, so I fail to reject the null hypothesis. I do not have enough evidence to show that, let's see, the professor's pass rate is less than I should put the word shown than thought, than previously thought. So I'm just answering that last question. Okay? Alright, so let's see. Got all that. So let's talk real briefly, real fast about alpha levels. Alpha levels, this is the number at which we reject the null hypothesis. Or for all the this is the number where we reject the null hypothesis. So that for all the previous things that we've done so far, it's that 0.05 that we talked about. However, if we want to, if it's called for, we can change that number to, say, make it easier or harder to reject a null hypothesis. So let's say I want even more evidence to show that I can reject a null hypothesis. Well, I can lower it to say something like 0.01, and if it still rejects, it's that much more justified to reject the null hypothesis. I can also increase it if I really want to reject the null hypothesis to make sure it works. However, it kind of decreases the strength of my argument because I'm basically trying to really get rid of it. Okay, so how does this work? Well, really, just at the end of a situation, it's going to tell you what it is at the alpha level that you want. So Duracell claims that 93% of its batteries will last longer than 7 years. A study is done on the random sample of 1,000 batteries, and it's found that only 91.5% of the batteries last longer than 7 years. Is this enough information to determine that the percentage of batteries that last longer than 7 years is less than advertised at a 0.01 alpha level? Okay, so so we still went through the whole thing. So P is still 93% because 91.5% is based off of the sample. And so if I go to step number 1, random, and I might have not written the word random. No, it is random sample of 1,000 batteries. So, okay, so or you can just say, you don't have to put I. You just say 1,000 batteries are chosen at random. 2, 10%. We can say 1,000 times 10 equals 10,000. So 10,000 batteries is less than all batteries created ever. And 3, success failure. So let's see. My percentage was 93. So 0.93 times 1,000 gives me 930, which is greater than or equal to 0. 0.07 times 1,000 is equal to 70, which is greater than or equal to 10. And now that gives me enough to move forward. Okay. So, step number 2. So I get null and alternative. So we're going to say P equals 0.93. And then it says, is this enough information to determine that the percentage of batteries that last longer than 7 years is less than advertised at a 0.01 alpha level? So it's less than, so I get less than 0.93. Okay, then actually I'm going to not use that color. You get out of there. Step number 3. We're going to do the square root of 1 minus 0.93 times 0.93 over 1,000, which gives me 0.0081. So let's see, the other percentage was 0.915. So 0.915 minus 0.93 divided by 0.0881 gives me negative 1.85. And if I go to my z-score chart, let's see, that gives me negative 1.85 is 0.0322. Okay, So now here's where it gets interesting, and the alternate hypothesis. Let me flip that back over real fast. The alternate hypothesis is less than, so I leave that alone. Now here's where it gets interesting, because if this was still at 0.05, then we would be rejecting the null hypothesis. However, that being said, since we've lowered the alpha level to 0.01, we're now going to, at this stage, instead of weighing it against 0.05, we weigh it against 0.01. So 0.0322 is actually greater than 0.01. So because we're using a 0.01 alpha level, we are still going to fail to reject the null hypothesis. So I fail to reject the null hypothesis. I do not have enough evidence to show that batteries will last longer. Wait a minute. Show that let's see. Duracell batteries. No, let me redo that one more time. That the percentage of Duracell batteries that last longer than 7 years is less than advertised at, and if you want to add this, some people do, at a 0.01 level, because technically speaking it would have rejected at a regular level. Okay, so there's that one. Let's look at one more, and then I'm going to show you how you can do these calculations in Statcrunch, and then we'll be done. So situation 5, the national average for left-handed people is 13%. A random set of 900 people were polled, and 14% are found to be left-handed. Is this enough evidence to show that the percentage of left-handed people was different at a 0.08 level? Okay, so step 1. So random. Let's see. 900 people are taken at random. Number 2, 10%. 900 times 10 is equal to 9,000 is less than all the people. This is national, so in, we'll just say our country. I guess technically I didn't say which country I am currently in. I'm currently in the United States, but you know. 3, success, failure. So let's see, it's 13%. So 0.13 times 900 gives me 117, which is greater than or equal to 10. And then we're going to do 0.87, which remember is once again 1 minus 0.13. So 0.87 is 783, which is greater than or equal to 10. Okay, and then And then I have a null. I have an alternative hypothesis. My null is going to be p equals 0.13. My alternative is going to be, let's see, evidence shows the percentage of left-handed people is different. So different is just not equal to. Okay. Step number 3. This is actually going to present an issue that comes up rarely, and I don't really give them out on tests, but it does come up sometimes, and I'll show you in 1 second. We're going to square root of 1 minus 0.13 times 0.13 over 900. So I get 0.0112 and then so I'm going to do 0.14 minus 0.13 over 0.0112. And so that gives me 0.89. Okay, and if I look up my z-score, that gives me 0.8133. Okay, so now, here's something that happens every now and again. The rule for not equal to is to multiply by 2, but as you can see, if I multiply this by 2, it's going to be over 1. And so you can't do that. So when the p-value, we'll call, I guess you can call it the p-value. The p-value will be, well, you would be, but p-value will be over 1 when multiplied by 2, you have to subtract by 1 first, because the p-value is supposed to be the ends of the normal curve, and this is clearly more the middle of the normal curve. It shouldn't be this big, basically. 1 minus 0.8133 is 0.1867. And then, so now I can do 0.1867 times 2. So 0.3734. And so 0.3734 is my p-value. Step number 4. So I have 0.3734, and my alpha was 0.08. So this is definitely greater than 0.08. So I fail to reject the null hypothesis. Let's see, I do not have enough evidence to prove the percentage of left-handed people is different. Okay. Alright, so now the last part of this is going to kind of look at how to put this in Statcrunch. So real fast, I'm going to bring up Statcrunch if it wants to come up. Oh, didn't want that actually. Let's minimize that guy right fast. And oh wait, here we go. Okay, so Statcrunch. Open Statcrunch. Okay, so to get to this particular test, you're going to go to stat, and you're going to go proportion stats, and you go to one stat, and you're going to go with summary. Now, once again, like when we do confidence intervals, you're going to have to multiply it out. So, for instance, if you look at the very first one, the very first situation where we're talking about giant foods, the 93%, I'm sorry, this one has to be the sample. So the 90% from the sample, you would literally have to do 0.9 times 500, which would give you 450. So you have to put down the number and not the percentage. So you put 450 here, and then it'd be over 500. Okay, and then you're going to make sure this is clicked on the hypothesis test. And so what we were testing for was 0.93. And my thing here was not equal to, but you can change it to less than or greater than. And then you just hit compute. And that gives you a p-value, which is pretty much what we got. So it does the multiply by 2 and everything. So like the last one that we're talking about, which was also a not equal to. So we could go to stat, proportion stats, one sample with summary. So this number 5, the situation 5 that we're talking about with the left-handed people. So we have 14% of 900. So that was 126. So number of successes is 126, and number of observations is 900. And then we want to make this 0.13, and it's not equal to. And we hit compute, and yep, that's pretty close to what we got. I got 0.3734. This is 0.3724. It's slightly more precise because they kind of take it out to a larger decimal. And that proves that it's definitely not going to get rejected by a 0.08. In fact, you'd have to put that alpha level up pretty high if you'd like to reject it. Okay, and that's it.